So, hello everybody, this is Iftikhar Ahmed back with my new video on electric charge and field. Today we'll learn about the Coulomb's law. You see, this law will help us understand how the charge particle will interact with each other. So this law is not mainly given by just Coulomb, but the final touch-up for this law was given by Coulomb. Actually, there are a few more scientists also worked on this law, but the final touch-up was given by this scientist named Coulomb. That's why we call it as Coulomb's law. So, in this universe, we have charges. So these charges, we have studied that these charges will exert force on one another. So the charges which are having same polarity, same signs, like positive charge and the positive charge, if both are positive, they will repel each other with some force. If the charges are of different polarities, means negative and positive, they will attract each other with some force. That force is responsible for the charge present in the body, present in the particle. We already studied those things. Now this law will help us to find out with what amount of force the particles are getting repelled with each other, or the particles are getting attracted towards each other. This law will help us to find out the magnitude of the force. So let's get started. Let's suppose that I have two charges, Q1, let this be as positive charge, and I have another charge, Q2. This is also positive. It does not matter whether you're taking a positive or negative, but for now I'm taking both as positive. The distance between them, they are separated by the distance from this particle center to this particle center. The distance between them is small r. So because these two charge particles are positive charge in them, that's why they will repel each other. So the force experienced by the charge 1 due to charge 2, okay, the charge 2 will have some impact of it on the charge 1, and because of this impact, due to the force due to the charge 2, the charge 1 will get repelled towards this way. So this is the force on 1 due to this charge particle. So this 2, the next number is for due to which particle the force is there. So the charge 1 is experiencing force due to the charge 2. Okay, so similarly there will be, so this is having direction this way, so force is a vector quantity, we can write it as F bar. Okay, now similarly the charge 1 will have some impact on charge 2. The charge 2 will experience some force. That charge is getting exerted because of this charge Q1. So the force will be in this direction, and that force is experienced by 2. Due to what? Due to 1. That's why the second digit is standing for due to which charge the force is acting. Okay. Now, so this law tells us that the force will always act along the line joining the particles. The force will always act along the line of joining the particles. So the line of joining these two particles is this. So the force experienced by 1 due to 2 will be in a line joining the particles. Along this line the force will be there. It is not like a magnetic force. If suppose you have a magnet, north pole, south pole, if you have some particle, any substance who is magnetic, who can get affected by the magnetic field, will move something like this. It will not move in a line, so it is not a force which can act along the line joining the poles. So the electric force experienced by one or experienced by two due to one or two will always be in a straight line, will always be in the line joining the two particles. It won't be like that. This particle is here, the other particle is here. The force due to this particle on that particle won't be in that direction, won't be in this direction, won't be like this. It will always be, if they have the same polarity, the effect of the force will always be in a line. So this is the line. The force will be always be either away from it if they are having opposite polarities, or towards the this charge if they are having different polarities. Same polarities away, different polarities towards it. So it will always act in a line only. It won't behave as magnetic force. Now the next thing is that the force, whatever the force the particle 2 is experiencing, the same amount of force the particle 1 will experience. Okay, but the thing is, they both have equal magnitude but opposite in direction. You see, the force 1 2 is equal to 2 1 but with a negative sign. This negative sign is coming because they both have different direction. If this is in this direction, if this was also in this direction, then we can take them as, then this minus sign won't come because they are having opposite directions. That's why this minus sign is coming, and the force of the magnitude will be same. Okay, now if I write it in magnitude form, in the mod form, it will be 2 1 will be equal to 1 2. 1 2 will be equal to 2 1. So this is the consequence of the third law, Newton's third law. The forces are having equal magnitude but opposite in direction. Okay, so this is from, you can say it, you can relate this thing from Newton's third law. That's, you can see how beautifully Newton's third law is merging here. Okay, now the one more thing is that the force between the charged particles is inversely proportional to the square of the distance between them. The force is inversely proportional to now there's one more thing that you can see from this law is the force is directly proportional to Q1 Q2. The amount of charge present in the particle will increase the amount of force exerts. Okay, if whatever the force of exertion is there due to this particle or due to that particle on the other particle will always be proportional to the amount of charge present in the body, present in the particle. If the particles are having more charge in them, they will exert the force with more they will exert more force on the other particle. Are you getting my point? Same as the gravitational force. If you have huge masses, if the masses are huge, the gravitational force of attraction between them will be more. So here the charges are responsible for this electric force. So if the charges are more, the force of attraction or the force of repulsion between them gonna be more. Are you getting my point? So that's how F is directly proportional to Q1 and Q2. There's one more thing that you can see from this law, that F is inversely proportional to the square of the distance between the particles. the square of the distance between the charged particles. You see, this law is called the inverse square law. We have seen this kind of relation in the gravitational force also. The gravitational force follows inverse square law, and the Coulombic force will also follow the inverse square law. What is actually a inverse square law? Inverse square law, to get the feeling for it, suppose if I increase the distance between the particles, distance between the charged particles by 2, by what amount? I'm increasing it by 2, then the force will decrease. So because they are inverse, the force has to decrease, but the force is getting decreased by, so the present force after increasing the distance by 2, the present force, I'm representing it with F dash, will be equal to the force which was there when the distance was just 1, initial force, divided by the force will get decreased by 4 amount. If the distance will increase by 3, the force, the new force will be less than 9 times less than that of the initial force. So you are seeing some kind of pattern in here. So this pattern is nothing but the inverse square law. The relation between F and R, with this we can say that F is inversely proportional to 1 inversely proportional to the distance square, the distance between the particles square. So this is called the inverse square law. The same is true for the gravitational force also. Okay, now if we add them all together, if I take all the things into consideration, to remove the proportionality constant, I have to take a constant in here. That constant is the kappa or the K. The K is K Q1 Q2 by R square. So this is the final expression for the Coulomb's law, where K is the proportionality constant. It is equals to 1 by 4 pi epsilon. This epsilon is called the permittivity. What it is? Permittivity. What it is actually, and why the constant is coming into this formula. What is actually meaning of this constant? The epsilon is the permittivity, and there's one more thing called epsilon naught is the permittivity of free space or air. For free space or air, this epsilon value will be epsilon naught. It means what? What is the what is the importance of taking this constant into this equation? How this constant gonna help me out for finding the force on the particles, on the charged particles? You see, if these two particles are in free space, the force will be like there is no medium between them, so there is no any kind of disturbance for the force to act on each other. The force can act in the free space easily. The penetration of the force from one object to the other object, the effect will be passed from one object to the other object easily. But if suppose the same two charges are in a medium, for example water, okay, in the water the medium is dense as compared to, like if you talk about air or free space, the force can penetrate easily from one object to the other object. The impact will be easily penetrating. But if you take a medium who is having some dense medium, for example water, the effect of the force on the other particle due to this particle will get decreased due to the presence of the medium. If the medium is more dense, the effect of the force will be less on the other particle due to this particle. For example, suppose me and the other person are fighting with each other. If I hit him like this, the impact of force will be more. Why? Because I am doing it in a free space. Or but if you the impact on the other person will be, suppose I am hitting him something like this, okay, but the same thing is happening inside underneath of the water. The force, so I am applying the same force, but the impact on that person will get decreased. Why the impact on the other person got decreased? Because now I am in a medium who is having more dense, as compared to air. In the air, the impact on the other person due to my punch was more, okay, because there is nothing to disturb me. But now I'm in water. The impact, the same amount of force is there, but the impact on the other particle got decreased. Because the impact got decreased, the amount of force will decrease. More dense the medium is going to be, the force will decrease. Okay, that's how this thing is in denominator. If this thing will increase, the force will decrease. Are you getting my point? So for air and for free space, it will be just epsilon naught. So this is this is the importance of having a constant in this equation. Are you getting my point? Now the value for this K is, for free space and for vacuum, is 9 into 10 power 9. Okay, what are the units? To find out the units, we'll use this expression. F is having force, so that is newtons. So this meter square will be here. So here meter square, and Q, and there's another Q. I said charges will measure them in SI unit as Coulomb. So Coulomb square. If I send it to here, it will be Coulomb square in the denominator. Okay, this is the unit for the K, and this is the amount, this is the magnitude for free space or air. They're almost equal. Now, in the competitive exams, based on the inverse square law, you'll get the question something like this. You have to, they'll give you some graphs in option A, B, C, D, and you have to identify which particular graph is perfectly describing the inverse square law. So this is the graph which perfectly explains, which perfectly represents the inverse square law. This F is inversely proportional to F is proportional to 1 by R square. How you're gonna represent it in a graphical manner? So see, I'll be having two axes, one for the distance between the particles, distance between the charged particles, that is I'm taking along the x-axis as R, and the other is the force between the particles, that is F, I'm taking it on y-axis. So this relation will give you a graph something like this. Now how to check whether this particular line will perfectly is perfectly representing this equation? Let's see. If I increase the distance, so initially distance was here, if I increase the distance by a small amount, you see I'm just moving a little bit towards the x-axis, not a big amount, but you can see from this expression, from this graph, is that the force got decreased by a bigger amount. Again, if you move just a little bit here, the force will decrease by a bigger amount. So that's how this particular line is the perfect suit for F is equals to F is proportional to 1 by R square. Okay, this is the graphical representation of inverse square law. So this representation works for both gravitational force as well as the coulombic force, like the electric force also. Okay, now we'll see the vector form of the Coulomb's law. So this is just a normal form. Now we'll see how to write the vector form of the Coulomb's law.